Hello, my name is Ishan Tamakar and I am going to present the demonstration for the Turtlebot3 simulation using open loop controller. First of all, I have this terminal window over here where I'm going to execute the Turtlebot3 gazebo environment, in which we'll see the Turtlebot in an empty world. As you can see, we have the Turtlebot, we have the empty world, and it's currently doing nothing. So one thing we can do is we can go back to the terminal and execute a ROS node called Turtlebot3. So this node will actually publish velocities and angular measurements for the Turtlebot. So this is the command over here, Turtlebot3 teleop. So let's give it a while for it to load. So yeah, it ran, and it's showing you that you can use the WASD keys to move around. So let's try that. So notice the Turtlebot, this tiny thing over here. We're pressing the keys and it is moving. So we have to be on the terminal window in order for the keystrokes to register. So if you get out of the window, we will not be able to move this robot. So let's press space key over here to stop the robot. And that was the teleop demonstration. For the second part of the demonstration, I have written a ROS node for open loop controller, which I'm going to run and control this robot to move to a certain goal location using open loop controller. So here we have a publisher that publishes to the command vel topic. We also subscribe to the autumn topic in order to get the robot pose, which we're going to plot later on at the end. And yeah, we have created all these attributes to keep track of the variables, the kinematic terms and everything. So we have a get current time in order to check the simulation runtime. We have a velocity profile generator function, which we have used to calculate the various kinematic terms, such as constant velocity during steady state motion, constant acceleration during the initial phase of the robot movement, and finally the constant deceleration phase. Using all of these 1 degree of freedom kinematic modeling equations and formulas, we get the velocity profile. And we also have a convenient plotting function that finally plots the velocity profile and the robot pose, which we store in these 4 lists over here as the robot moves in real time. So these lists will get appended as the robot is moving. And finally, this whole function will be called when the robot has finally stopped in goal position. In the timer callback, we have our main open loop controller code. So we check for the current runtime, and based on what phase of the runtime we are at, we will give it a linear velocity message of a certain amount based on the modeling that we did previously. So yeah, we have phase 1 is the acceleration phase, phase 2 for the steady state constant velocity, and phase 3 for constant deceleration. Finally, when it's reached the goal position, the robot will just stop. We also have a listener callback that always gets the current X and Y location of the robot. So we are not grabbing the angular bearing because this is a 1 degree of freedom problem, and we just assume it's facing forward at all times. In the main function, we just create an instance of the open loop controller node. We set the velocity profile, give it a goal location of, let's put maybe 5 meters, just to be make it long enough, and we start the simulation here, and we spin the node, the controller node, so that all the subscribers and publishers are running. And finally, on exit of the node, we shut down the whole system properly. So let's see this code in action now, shall we? Going back to our terminal window, looks like we already have our gazebo world running. So yeah, this is how we run the node that I just showed you. So let's go back to the Turtlebot, and started moving. So we put a distance of 5 meters, right? So here we have calculated these terms: constant acceleration, deceleration, phase 1 time is 3 seconds, and all of that. So looks like it executed properly, and the robot has reached the goal position and it has stopped. So hence we are showing the plot. So on the left hand side, we have the velocity profile showing you a velocity versus a time elapsed, and on the right hand side we have the robot pose. So this is not as predicted, because the robot was not facing the correct bearing, so we have to correct all that. Yeah, that's how we did it. Okay, we have the open loop controller demonstration. Here I will run the gazebo world again and wait for it to load up. So here we have the Turtlebot, it's not moving. We will run the open loop controller node now. And it will start moving towards the goal location specified right in front of it, which is 5 meters. So as you can see, the robot has started moving, and it should stop exactly or approximately at 5 meters. So yes, and it generates the velocity profile graph and robot pose graph, which is showing the current X and Y location of the robot, and it is bearing towards the right direction. That was my demonstration. Thank you for watching.